Welcome everyone to Statistics 115-215 class again, and today we're going to talk about hidden Markov model. There are statistical and machine learning algorithms. From the name, they sound so scary and difficult, but once you learn the simplicity and beauty of it, you will enjoy using it for many problems, and hidden Markov model is one such problem. So let's start. Before we can talk about hidden Markov model, we need to understand what is a Markov chain. IID are independently and identically distributed events. So these are events not correlated with each other. So the current event has no predictive power of future event. For example, if some family had a boy, the probability that their next child is going to be a girl is not dependent on the previous child. So it's only the probability of having a girl. The next question, say if I have a coin and I flip the coin, I got a head, what is the probability the next coin flip will be a head again? We know that as IID process, it's just the probability of having a head, regardless of what the previous coin flip is. The third question example is, if I have a dice, knowing that the previous dice I got a 5, what is the probability of getting a 1 this time? And you know it's just a probability of 1. And so the previous die toss is not influencing. And so these are independently and identically distributed process. In contrast, discrete Markov process, usually we have a few distinct classes, states, for example, S1, S2, S3, and we have regularly spaced discrete times like time 1, 2, 3. So a discrete Markov chain are situations where the future state only depends on the present state, but not the past to get here. Which means, for example, in this case, the probability that at time t that we're going to see a particular state, it only given all the previous states, is only dependent on the probability at the previous one state, one time, and all the previous time doesn't really matter. And this is the probability given by this probability distribution, which is called a transition probability. So I'll show you a few examples in here. By the way, the transition probability of all the different situations need to all be over 0 and less than 1, and they add up to 1. So let's look at some examples. For example, if in so the states, so this is an example. So if somebody in an exam, they passed the exam, in the state will be 1, and if they fail the exam, the state will be 2, and the discrete times will be the number of exams, first exam, second, and third. And the state transition is like this, which means that if they passed one exam, the next chance they will have 80% chance of passing the exam again, but 20% a chance that the next exam they will fail. However, if they fail the exam, the next chance they have a 50-50 chance of passing and failing. And so you can see here, these two numbers need to add up, because we know that the previous exam is a pass, and the next one, whether they pass and fail, they add up to all the possibilities. And if they fail the exam, the next exam, whether they pass or fail, they also need to add up to 1. So this is the transition probability, and we'll be using a lot of that. And so let's look at this. Given some student has taken 6 exams for this, say, semester, and their grade is pass, 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 fail, fail, fail. What is the probability that in the next exam the student will pass? And you can see this is given by this probability distribution, which is we are asking what is the probability on the 7th exam the student will either pass or fail, or in this case state 1, which means they will pass, given A is the given this transition probability, and knowing that we have observed 6 exams before where the student has pass, and fail. This, if this is a discrete Markov chain, it would mean that it doesn't matter what the student did early on, the chance that they will pass the next exam will only depend on the previous exam, in which case the student failed. And so we look up the transition matrix. We say, okay, if the previous exam the student failed, they have a 50-50 chance of passing or failing. Therefore, the chance that they will pass is 50%. So that's the first example. The second example of Markov chain is, of course, this is just, we made up this scenario. So the discrete states are, this is a weather example. So one, it's a raining day, and second is a cloudy day, and the third is a sunny day. And the discrete times is day 1, 2, 3, the weather of each day, the time. And the state transition probability, we're making up this state transition probability, and you can see here every row, they need to add up to 1. And the first row means if the previous day is a rainy day, what is the chance the next day is going to be raining, cloudy, or sunny? In this case, 0.4, 0.3, 0.3. And if the previous day is cloudy, the chance the next day is going to be rain is 0.2, cloudy 0.6, and sunny 0.2. If the previous day is sunny, the probability the next day is going to be rain is 0.1, cloudy 0.1, and sunny is 0.8. So this, again, is the transition probability. And so we have a question here. Given that at day 1, we have a 3, which is a sunny day, the question is, what is the probability that the next 8 days of weather is going to be like this? And so we write it this way. Given that in day 1, we have sunny weather, and given this whole transition probability matrix, we're asking the probability of the next 8 days of weather according to this. And this is based on the transition probability as if we know the previous day is a sunny day, the next day being a sunny is a transition A33, which is 0.8 in here. And then so that's the sunny to sunny, and then this another sunny to sunny in here, again 0.8. A sunny to a rainy day is A31 is 0.1 in here, and then rainy to a rainy is here 0.4. A rainy to a sunny here is A13, which is sunny to a rainy to a sunny is 0.3 in here, and A32, and finally an A23. So you multiply these probability matrix, you will get some numbers here. So that's the second example. The third example is if we have a coin, there are a number of states. Supposedly we're just trying to use different coins to make different flips. And so supposedly we have a fair coin, and also we have a biased coin or unfair coin. So that's fair coin is F, biased coin is B. The different times is we use the coin to make the flips in here. So these are coin flip 1, 2, 3. And we have a initial probability, which is the probability that the first time we pick a coin as a fair coin is 40%. And the probability that we happen to pick a biased coin in the beginning is 0.6. We are making up these probabilities. I just want to show you an example. And the transition probability, you can write it as a matrix, but in this case, since we have only 2 states, we can also use this kind of a diagram to show. For example, if I am using a fair coin, the likelihood that the next time I do a coin flip, I'll use the same coin is 0.9, but then there's 10% chance I'm going to switch to a bias coin. But if I'm using a bias coin, then the chance that the next coin will be biased again is 70%, and then I also have 30% of chance switching back to the fair coin. And so this is the transition probability. And so we can, given the transition probability, we can now ask, what is the probability that we're going to see the following string of coin flips, given the transition probability and the initial probability? So here, how do we calculate that probability? It's first we have to pick a fair coin in the first place, and then from there we'll go to fair to fair, fair to biased, bias to biased, bias to fair, fair to fair, fair to fair, and fair to bias. And so these, the remaining ones are all transition probabilities, and you can just multiply their probabilities together and you will get a number. And so that's the probability given the initial probability and the transition probability. So that's Markov chain. So we talk about Markov chain. What is a hidden Markov model? So hidden Markov model is different in that we still have this coin flip example. There is a fair coin, which is in this case 1, and an unfair coin, which in this case is 2, and we're switching back and forth to do coin flips using different coins. So the coin transition is a Markov chain. However, we're observing, what you are observing here, instead of the coin, we're observing using that coin, we make a coin flip and we ask, did you get a head or a tail? So in this case, the head and tail is the actual observation, but the states we use, in this case, we're using bias coin to make the flip or a fair coin to make the flip, and so on. So we're using different coins to make the flip. So the probability of a head and tail depends on the coins you use because they have a different probability of giving a head or a tail. The observation of head versus tail is a hidden Markov chain because if we don't tell you the hidden states, so in this case, I'm trying to use a coin to make a flip, but the coin is in my hands and I'm hiding behind the table. Instead, what you can see is I'll just use the coin, I flip, and I'll tell you I got a head. Next time I use a different coin, I'll tell you I got another head. And then I shift between the coins. I only tell you the observation of head, head, tail, tail, head, and so on. I don't tell you what is the coin I'm using. And so the coin state is hidden from the person who is doing the observation. So that's called a hidden Markov model. So what are the elements in a hidden Markov model? Again, let's look at elements of hidden Markov model using the coin toss example. We have the number of states. In this case, the hidden states are the coins we use, which is fair coin and bias coin. We have the number of distinct observations, what we can actually observe. In this case, it can either be a head or a tail from the coin. And then we have another set of parameters. The first is the state transition probability, which is what is the probability of, say, if I'm already using a fair coin, the probability I will use another fair coin is 90%, but the chance I will flip to a bias coin is 10%. If I'm already using a bias coin, I'll have a 30% chance of changing to a fair coin, but 70% chance of staying in the bias coin. So that's the transition probability. And we also have this initial probability, which is the probability of giving head or tail given the coin I'm using. So in this case, if I have a fair coin, I'll have a 50-50 chance of giving out a head or tail. But if I'm using a bias coin, you can see it's biased because 80% of the chance I'll get a head and 20% of the chance I'll use a tail. I'll get a tail. And then we have an initial state probability, which is what is the chance that the first coin I pick is gonna be a fair coin or a biased coin? In this case, 60% chance I will pick a fair coin, a biased coin in the first place. Okay, so that's the element in a hidden Markov model. What is this useful for? So hidden Markov model is a very useful machine learning algorithm. You can use it in the stock market. For example, imagine there are ups and downs in the market. You observe the stock price going up and down and up and down. But even though there's fluctuations, if we observe the overall trend, if it's overall going up, we know in the market it's called a bull market. But even if individual day there might be up and downs, if overall it's kind of going down, then it's a bear market, it's going to a recession. Right? So despite the daily ups and downs observed, because the big trend of the market is the hidden states of being either a bull or bear market, then we have the observed stocks going up and down. Another example is speech recognition. So in this example, we are trying to say some words or phrases, the actual sentences. So these are the Markov chains. They follow certain rules of grammar, right? Certain words follow other words. The sentence usually have a structure. You have a subject, a verb, and an object. But then that's not readily recognizable by a computer. What the computer sound is taking is the sound that's given. It's heard. Okay, this person said some vowels and consonants, and it's trying to guess what the words are that's hidden from the computer. And so that's speech recognition. Also signal processing. So supposedly we have some people sending a signal over internet. Initially the signals out is 0 or 1, but this signal might be converted to a analog signal of some values, continuous values, to be sent over the wire. And on the receiving end, because there's fluctuations, we might see some continuous values, and the computer at the receiving end will try to guess, is the original source signal a 0 or a 1? If I receive a signal of, say, 0.8 or 0.9 or 0.98 over a string, so the computer is receiving a signal like this, right? So it's trying to guess, is this 0 or 1? And actually, hidden Markov model is also used in bioinformatics, and we will talk about that after we explain the whole application, the models.